So today is, of course, yes, Pi Day 31416. We're going over the 3D FIP quiz. So in the first one, we've got, basically this is just like the sample problem you had. We have a bungee jumper. I guess the bungee jumper is you. And I asked you for both total potential energy and net potential energy, kind of to illustrate the difference there. And so to remember that, so the way that I kind of rationalized this for myself was the total potential. Geez, Louise Moser, is gravitational. Peg and P. Yeah, it's gonna be a long day. Thanks for your vote of confidence. Is the sum of the magnitudes of the gravitational and the elastic. So I think you use this symbol in math, the 2 bars meaning absolute value. So, you know, just the magnitude of them, and we're not concerned with what direction they're in. We're not concerned with, you know, the fact that they're opposing one another, where the net potential energy would just be the sum of our peg and our peat. And that takes into account, of course, the fact that, actually I could make that a simpler one move, couldn't I? And I just wrote total again, didn't I? Yes, I did. Cut, 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 cut. Okay, where the net is equal to the sum of the peg and the peat. So you're taking into account the fact that they're opposing one another and using signs on them accordingly. So, okay, so for either of them, we first have to figure out the magnitude of the potential energy due to gravity and the potential energy due to elastic forces. So for the gravitational potential energy, since we're interested in the moment at which this crazy person stops falling, we want to look at that lowest point. And we said that the bridge was, what, 55 meters high? 55.0 meters. And the extended length of the bungee was 42. So the difference between those is 13 meters. So basically, at the point when they stop falling, there is 13 more meters that they could fall. And so that's the height above reference point. And we're using the surface of the water as a reference point. That's the height above reference point. So this is equal to 75 kilograms times 9.81 meters per second squared. Let's shrink this a little bit. The negative, yeah, you know what, let's talk about that. Okay. So for right now, let's say we're not, because we're looking at the magnitude. And then I think the easiest way to handle that, 13.0 meters, is to look at the direction of the possible work being done and know that here it's down, so the work would be, or the energy would be negative. It would be downward. Well, though, wait a second, because that gets us into, you know, negative energy sounds like there's not a potential to do work, and yet there is. Yeah, yeah. I don't have a beautiful answer for this. I'm sorry. Okay, so let's stick with the magnitude for now. And what we get for peg is 9564.75 joules. And we know that that energy is something that would enable this object, this bungee jumper, to go downward, to do work downward on an object. So we'll just leave it at that for right now. And then we have the elastic potential energy, 1/2 kx squared. And our k is the spring constant, so that's an easy one. X is the difference. Let me move these back a little bit. X is the difference between the unstretched and stretched length of the bungee. And we were told that the unstretched bungee was 10 meters. So we've got an unstretched difference of 32 meters. So we have 1/2 of 65 newtons per meter times 32 meters squared. And for the value of elastic potential, we get 33,280 joules, and that potential energy would pull them back upwards. So that's potential to go up. So for our total, we're just adding the two magnitudes, regardless of sign, and we get 42844.75 joules. When we sig fig that, we have 3 sig figs to work with, so it ends up as 42,800 joules for the total potential energy. Now, if we think about the issue of net potential energy, and we think about that as a separate thing where we're taking the magnitudes because they're in opposition to one another, or we take the actual value in account, we end up with a net potential energy of 23715.25 joules, and so with sig figs that gives us a PE net of 23,700 joules. Okay. So obviously a lot more total than potential. And for net you would have to, obviously a lot more total than net. For net, you would obviously also want to indicate in which direction this energy would cause the object to do work, and it's upward, upwinds. There was a lot more elastic potential energy there than there was gravitational. Questions, comments, concerns? Yes, sir. There we go. Okay, so this is a really simple problem. We have a spring with some given spring value, and how much potential energy is there? In other words, how many joules of work can this thing do on you if it snaps back and hits you? And it's a pretty stiff spring because it's got a spring value, a K, of 500 newtons per meter. That is not, we're not messing around. And what we want to know is the potential energy that is the elastic potential energy. X is equal to 4 centimeters. Almost everybody got this perfectly right if only they had converted units. So that's a simple one. Easiest way for me, it's kind of the dummy version of this. I always just fall back on powers of 10. So 4 centimeters is 4 times 10 to the negative second meters. And that's so much easier than setting up a factor label. I mean, you can get that by setting up a factor label, but I find it easier to just do that. So what you get, and of course you had to square that, which was the other thing that I did see people forget, what you get is 0.400 joules of energy. So it's a really stiff spring, but that's not all that much potential energy. You can go back and think about how much force it would exert on you if it did whack you. It's not being extended that far. I mean, 4 centimeters is like, what, that? Yeah. Yeah, it's, well, there's a centimeter to, yeah, okay, about like that. So, okay. Okay, so this was the throwback to 4C, and I told you I'm going to give you a problem like this on the test, so I want to have lots of chances for you to practice it. And we have a box on a ramp being pulled by some poor schmuck, and we've got all these forces assigned. So force of the puller is 456 newtons. We know that the box moves 8 meters, and I'm ignoring sig figs as I'm just quicking this out. We have force of gravity on the X, force of gravity on the Y, and we have a force of friction, and of course normal force. you'll note that I asked in this the work being done on the box by the puller, the work being done on the box by gravity, and the net work. I did not ask about the force of friction, which was tricky and mean, but you had to remember that it was there. So when you get to doing the net work, you have to remember that there is also that frictional force acting on the box that's sort of retarding the motion generated by the force of the puller. So A, super easy. I don't know that that looks like an A. So work of the puller is equal to the force of the puller times cosine theta, where theta is the angle between the force and the distance, times d. And it couldn't be more straightforward. Cosine theta between the force of the puller and the motion is 0. He's pulling, or you're pulling, she's pulling, in the direction that the box is traveling. So we get 3648 joules, and with sig figs, for the final answer for that one, we would get 3600 joules as the work done by the puller. Okay. Now, the work done by gravity is the force of gravity on the axis where the motion is occurring. And in this case, that's going to be the x-axis. So we have to take sine of the ramp inclination, so FGX, cosine theta, where theta is the angle between the force and the distance, times the distance. So we end up with mass, gravity, sine of 24, and I'm just going to put that in there to keep it simple. The theta between the, it's 180. The theta, or the cosine here, that theta is 180, because gravity is exerting its force in the direction opposite that which the box is moving. So we get work of gravity as negative 1800, well, the raw answer, I'm sorry. Raw answer was 1755.638046. So we get negative 1800 joules is the work done by gravity. And most people, if you remembered to use gravity on the x, people got this without a problem. The net work was a whole different ball game. You can find net work two ways. Two ways without invoking work kinetic energy theorem. So, I don't know why that's still there. Okay, we'll just stick it there. So net work is equal to the net force, cosine theta d, or net work is equal to the sum of all the works. And you can do either one. I think I did sum of all the works. Yeah, I did work of kinetic friction, which meant you had to figure out the force of kinetic friction. Yeah, you could do it either way. You get the same answer with sigma. Okay. I don't know. Okay. So, to find force of friction, in this case force of kinetic friction, you have to do mu k Fn equals Fk, which means you have to do a sum of forces on the y-axis to prove that Fk equals, or I'm sorry, Fn equals F of gy. So we get our value for mu k, and if you do it using the sum of work, then net work is equal to 3648 joules up the ramp plus negative 1755, etc., which is down the ramp. And we had negative 1537 also down the ramp. So we end up with a net work of 350 joules, which I would just like to say, if you've ever pulled an object up a ramp or across something, I want you to look at this and think about, this is the net work. So he is, the puller, he or she is putting in 3,600 joules worth of work. And what they're getting out, when you factor out all of the other stuff, is 350 joules of work. That's really insulting. That's, you know, you're getting about 1/10 of your effort back in actual work done. And we could talk about efficiency all day long. Okay, so the last part of the question is the velocity of the box after it's moved 8 meters. Well, you have the net work. And let's shrink all of this. So this is the time to pull out the work kinetic energy theorem. So the net work equals the delta KE, or 1/2 mvf squared minus 1/2 mvi squared. And we have everything we need there, and we're just solving for VF. So if we do this algebraically, net work plus 1/2 mvi squared times 2 divided by m square root equals VF. Do you want to see the algebra step by step? We're good? Okay. So you get a VF of 3.7856 blah blah blah. We get 3.8 meters per second is equal to VF. I was about to write meters per second squared. You caught me. So 3.8 meters per second. That's it. Questions, comments, concerns?